Hi, my name's Mike Milner. I'm a senior consultant with Tomson Consulting. What I'd like to do briefly this morning is just to talk through some of the potential energy reducing opportunities and how to assess those at your sites. It's not going to be a comprehensive presentation in terms of all the techniques and all of the things that you can look at, because there just isn't time. However, what I'd like to do is to give you an overview of the sort of opportunities that I see throughout my sort of working days, and to give you at least an insight into some of the tools and things that you could do to identify what are quite cost-effective ways to reduce energy. And so I'm sure you're very acutely aware that energy costs have increased substantially. So on average, business electricity costs have increased by 57% in the last year, and gas has increased by 86%. Although the government has announced an energy price cap, that is not going to last, or is unlikely to last beyond March 31st next year. So now is a really good opportunity to look at what there may be at your sites to reduce energy consumption and costs, because from experience, the cheapest and also greenest energy is the one we don't use. So in common with most of the sort of business management, if you can't measure it, you can't manage it. So if your electricity and gas and other utility bills are based upon estimated readings denoted with an E after the reading, then please do start to take regular meter readings. Quite a useful thing to do is, if your site operates on a daily basis, is to take meter readings last thing in the evening and first thing in the morning, or at the end of the working week and the start of the new working week. That way that you get an idea of the consumption and therefore cost incurred with energy when you're not at site or when there's no production going on. You can also take and systematically record regular meter readings as well, on a weekly or a monthly basis, and compare those to the quantity and cost production or occupancy. A little bit of homework here. So your electricity and gas bills will be rated on the number of kilowatt hours, kWh, and that's a measure of energy consumption over time. And that, so if you're talking about the units of energy, 1 watt is the rate at which energy is transferred per unit of time, and 1,000 watts is a kilowatt. And if you're using 1 kilowatt in an hour, that's going to be 1 kilowatt hour, which is now costing lots, and the cost of that is increasing. Just as a couple of very simple examples here, and this is how you could go about quantifying the amount and cost of electricity used for certain things around your site. If you have an electric heater and that's rated at 1 kilowatt, and that's left on continuously for a day, 24 hours, then that would consume 24 kilowatt hours of electricity, which would cost £6 a day, assuming the electricity is costing 25p per kilowatt hour. Similarly, if you've got 10 electric lights and each of those is rated at 50 watts or 0.05 kilowatts, and they're left on continuously for 10 hours a day, then that would consume 5 kilowatt hours of electricity, which costs £1.25 a day, and over a 250 working day year, that would cost £312. So those are the sort of things that you can do if you know the rating, so the number of watts or kilowatts a particular piece of equipment uses, and the length of time it's switched on during a daytime period. Your electricity bills will contain somewhere on them this sort of information. So this is important. What this shows you is this is the unique number for the electricity meter at your site. And if you've got more than one meter, there will be more than one unique number. Always starts with an S, and it's always got a string of numbers after it. The important one here is the first one. Because it's 00, it means that you should be able to request and receive half-hourly electricity meter readings for that meter, which is really, really useful for looking at consumption over time. The other two numbers here, this is on a different electricity tariff, whether it's during the day, which is the 17-hour period between 7 in the morning and midnight, or overnight, the 7-hour period between midnight and 7. And what that does is it shows you the amount of consumption during the day and the amount during the night. Now, what you can do straight away is a simple thing here. So you can divide the quantity of electricity consumed either day or night by the number of hours and the number of days during that billing period. So dividing 11,600 and a bit by 7 hours and 31 days gives an average consumption of about 53 kilowatt hours per hour electricity. And if you do the same for the electricity that's consumed during the daytime period, so it's 17 hours a day, 31 days in that year, you get the same answer, 53 kilowatt hours per hour. And that immediately shows me, or gives me an indication that there may be electricity being consumed overnight when it may not need to be done. So what's being consumed overnight and why? Looking at similar information here, so this is just sort of monthly electricity meter readings at a site which had 3 different tariffs. So red line is during the weekday, this is weekend and evenings, and this is overnight. The biggest consumption in the winter period was overnight. So immediately you ask the question, why at this particular site, which only operated Monday to Friday, sort of 8 till 6? The answer was portable electric heaters, although the site is heated by gas, and external lighting. Returning to the half-hourly electricity data, once you've got that, you can do some simple analysis on that in Excel. You don't have to be a statistician to do this, and there's several things that I would look at here. So what we're looking at here, this is time, so midnight to midnight, and it is the quantity of electricity being consumed in any half-hour period up here. So 3 things. Firstly, consumption which is happening all of the time. Remember, this is Christmas week, so with the exception of these 2 coloured lines, the place is closed. So this is what's called the base load consumption. This is happening all of the time, regardless of what activities are happening at site. And this comprised, at this particular site, about 30% of the total, so about £48,000 worth. So it raises the question, what's being used and why does it need to be on? The other 2 things here are the regularly occurring increases in consumption. What are they for? What are they associated with? Do they have to be on? Can they be better controlled? After looking at bills, it's a good opportunity to take a walk around the site and all of the bits of the site that maybe you aren't so familiar with as well. Take a walk at quiet times before or after production, or during breaks, and see what's left on. So this cartoon here is showing all the lights being left on, Christmas, like a Christmas tree. This is an example here, which I quite frequently see, of all the conveyor belts being left switched on during break times, which soon adds up over a day and over a year. And this is external lighting, although you wouldn't know it because it's covered in dirt, just left on continuously. If in your roof space you have no, in this example, or patchy, limited, poor quality insulation, that's an immediate opportunity to roof space heating. Similarly, if you've got radiators which are obscured by goods or coats or tables, either can they be switched off or can the things be moved away from the radiators. A lot of heat can be lost from a building or a space through gaps around doors, gaps around windows, holes in walls, etc., etc. This is usually a very cost-effective opportunity. This is actually the front door of a hotel, which is going to be very drafty. An industrial setting here, so a high roof, and the idea was that these heaters around the outside are keeping the goods which are down here at a nice even temperature of about 12 to 15 degrees. In effect, what's happening is the heat is just rising up from those heaters and accumulating in the roof space. So the roof space was about 28 and the ground space was about 12 degrees. So redistributing the heat there is going to mean that you're going to reduce the amount of gas that's being burned to maintain the whole of that space at the desired temperature. If you've got a boiler like that, it should be in a museum. Looking at pipework insulation as well, this is was a new installation. Absolutely no insulation fitted on any of the distribution pipework, which was internal and external as well. So the heat losses will be significant and substantial. Somebody's had a go here at fitting insulation, and it is a good attempt at doing this. However, there still remain significant gaps in the pipe, and bearing this in mind, is just a very short subsection of a network, and also the insulation is quite loose. It's much larger diameter than the pipework, so there still will remain significant heat losses from that. Turning to hot water heating, and this could be for process heating, hot water, or it could be for domestic uses, or both. These are just 3 examples of the not so good, the not great, and the on the left here, the downright ugly, where there's absolutely no insulation fitted to the hot water heating, and this is the external wall of a tin shed. So another giveaway here that there's significant heat losses. This was in a cupboard, and it's being used as an airing stroke drying cupboard, and this is in a plant room where there's quite significant heat losses from the hot water tank here. So any of those are quite significant and quite and cost-effective opportunities to reduce heat loss and reduce energy consumption. And this is the classic, where there's heat losses from the pipe, but it's also comprising a health and safety concern as well. Ensure that your time and temperature settings are appropriate to need. So in terms of the temperature, and in terms of the time that the heat is required as well. Where you've got heating and cooling in the same space, ensure that there's a sufficient dead band between when the heating goes off and when the cooling comes on, to avoid the 2 systems competing against each other. Where you have building energy management systems or more sophisticated control systems for heating and ventilation, ensure that you or somebody else at your site knows how to operate them. So this is from a site that had a great system, lots of monitoring in place, but unfortunately nobody had been trained in how to use it. So the system was left on in its default settings, which was for 22.5 hours per day, 7 days a week, regardless of need of occupancy. Looking at lighting, I know it seems obvious, but maximize the use of daylight. This isn't a photoshopped picture. This is the same roof, 1 dirty skylight, 1 clean skylight, and it just shows you very, very well the difference in the amount of daylight that's coming through. Looking at that in the same sort of warehouse situation here, we've got racking which is under a skylight and racking which isn't. So here you had to have artificial lighting for it to be safe. Here you didn't. If there's lamps which are on but not emitting light, they're going to be consuming electricity but not doing the job that they should be. An example of behavioural change here is a great amount of natural daylight, lights are all on and nobody's at home, and there's over 30 lights in the picture. Looking at cooling now, this is an example of an evaporator in a cold store. There's reasonable amount of ice build-up here. This will reduce its efficiency. Now these units will be fitted with electric heaters to remove the ice from this, but paradoxically, if they're on too much, that will increase electricity consumption unnecessarily, or also increase electricity consumption associated with removing the heat that the heaters have put into that space. So can those defrost settings be improved? Can the control be improved? For example, can something like defrost on demand be retrofitted to those units? Where there are chilled spaces, it's important to ensure, and again this is a behavioural change thing, that the external doors to that chilled space are kept closed as much as possible. This is an example where it was just left open for the whole time. There's also strip curtains here, which are in use, but there's bits missing and they don't extend right to the floor, so their effectiveness will be limited. Similarly, if there are door seals in poor condition, or if the loading of the chill store or the cold store is somewhat haphazard like this in this picture, it will neither help the energy efficiency of the store itself or how well chilled those goods are in that store. This is a lighting and a cooling example here. So what we have is lighting which is left on continuously in a chilled store, and we've also have lighting which is over, right above and over chilled goods. So that is emitting heat right on the top of the chilled goods, and it's not providing any light effect. If you see ice accumulation on the refrigerant insulation, so this is outside of the building, then that will be increasing the energy consumption because you're losing the cold. And this is an example of what it looks like on a thermal image. So this is where there's missing insulation, and this is where insulation hasn't been fitted. So you see this is at -4, and it was on a day when it was about 12 to 15 outside, and then this is showing that it's -11. This is an example of where heating and cooling are on simultaneously. So there was heating on in a particular building, and simultaneously on a hot summer's day you're trying to cool that space. Water and hot water, and it could be for domestic or process purposes. If you can measure the flow rate, then you can measure how much water is being used. Now, a lot of sites now, they have cold water header tanks, and then they pump the cold water around continuously to the various points where it's being used. If you can minimize or reduce the flow rate of water that's being consumed, then that reduces the pumping energy, so the electricity required that's in a particular site. This is an example of just a regular flow, so this will be about 10 litres per minute, and this is one which has got an aerator fitted in the tap outlet, so this will be about 3.5 to 4 litres a minute. And it's not just water that you're using, it's also the heat energy as well that's associated with that. Some sites have water cooling towers as well, so which are quite often overlooked, and they're around the corner. And here we have an example where there's been a long-term leak, as seen by the staining there. So that's pumped, so that's using water, it's using power as well. Now, voltage optimization is something which is quite popular and has been quite popular over the last few years. It can lead to savings, but it needs to be effective. It can only achieve that if the supply voltage to that site is consistently high, and it will only make a difference to voltage dependent loads. So for example, that includes older types of lighting such as incandescent or linear fluorescent lighting, and where you have fixed speed motors, but you also need to consider the impact of motor losses as well and the efficiency of motors. It's not going to make any difference where you've got variable speed drive motors and pumps or thermostatically controlled heating, because that will just take longer to achieve the temperature if you reduce the voltage, or companies where you've got an on-site transformer and you should be able to control the voltage locally. To understand its potential, I'd certainly recommend analysis of the site electricity data, so the site voltage over time, and to survey what the voltage dependent loads are at the site at the time of survey and at the time going on as well, and also to obtain ongoing monitoring and validation of the predicted benefits of voltage optimization. As we've seen from some previous slides, there are often plenty of examples of where behavioural change, so switching things off or improving the control, can have significant savings. So example here, we've seen the conveyor belt before being left on. This is commercial kitchen, gas burners being left on at a low level just in case. This is again commercial kitchen, the gas salamander grill with nothing left on it under it just in case, and the restaurant pass with the 3 heat lamps each at 500 watts with nothing left underneath them for extended periods of time, just in case. So there are a lot of good examples of stickers and publications and posters and competitions to encourage people to change behaviour with respect to energy. However, quite often the downside of that is people feel hectored or put upon, and it leads to very little lasting change. Behavioural change in itself is quite a complex topic, but where it's done, and it's done well, it can achieve savings between 5 to 7%. It does take time. It takes consistency of approach, and it takes clarity of purpose, and it's something that can't just be done once and 1 week only. It's a continual process, and I would compare that with health and safety, and ensuring that the health and safety message is continually reinforced and reassessed throughout. Now, there's lots of good resources out there to help you with behavioural change, and there's a good webinar on the Business Energy Scotland website, and a link is placed here. So the sort of summary of doing all of these sorts of things and identifying and appraising and quantifying opportunities is a summary table which looks something like this. So this gives you an idea of the sort of things where there's saving opportunities, and the sort of likely or anticipated paybacks. This is a synthetic example which I've accumulated from lots of different projects here, but it just gives you a summary of the potential opportunities that there are at many sort of food producing sites, so comprising technology, management, behavioural change, all sorts of different things. So I hope that has provided you, it's been a very quick whiz through various aspects and various opportunity areas that I frequently see where there are cost-effective opportunities to reduce energy consumption and costs at your site, and I hope that's provided you with a bit of insight, and thank you very much for listening.